Equipment Lesson 1 covers X-ray tube construction, the physical hardware that makes diagnostic imaging possible. Before you can understand technique, dose, or image quality, you have to understand the machine producing the beam. We're covering the operating console, every component inside the glass envelope, the anode and cathode assemblies, heat management, and the quality control requirements that keep the tube working accurately. 14 minutes. Let's build it from the ground up. The operating console is where the radiographer controls three fundamental tube parameters. kVp, kilovoltage peak, controls beam energy. It sets the maximum energy of photons in the beam and determines penetrating power. Typical diagnostic range is 40 to 150 kVp. mA, milliamperage, controls tube current. More milliamps means more electrons crossing the tube per second, which means more photons produced and more patient dose. mA is set independently from exposure time on most modern consoles. The exposure timer controls how long the exposure lasts in milliseconds or seconds. MAS, milliampere seconds, is the product of those two values, and it represents the total dose quantity delivered. On digital systems, the console also displays the exposure index after every exposure. That number tells you how much radiation reached the detector. Monitor it on every case. Let's walk through the tube. On this slide you can see the complete cross-section. On the left is the cathode, the negative electrode. Inside the cathode sits a coiled tungsten filament surrounded by a molybdenum focusing cup. On the right is the anode, the positive electrode. This is where electrons strike and where X-rays and heat are produced. The space between cathode and anode is bridged by the kilovoltage, kVp, applied across the tube. That voltage accelerates electrons at tremendous speed. When they hit the tungsten target, 1% becomes X-rays, and 99% becomes heat. All of this happens inside a glass or metal envelope that maintains a vacuum. Without that vacuum, air molecules would scatter the electrons before they could reach the anode, and X-ray production would fail. Two components make up the cathode assembly. The filament is a coiled tungsten wire heated by a low-voltage current, typically 3 to 5 amps. This heating causes thermionic emission. Electrons gain enough thermal energy to escape the metal surface and form a cloud around the filament. This is the space charge. Filament temperature controls tube current. More heat equals more electrons boiling off equals higher MA. The MA station on the console selects which filament is active. Most tubes have two, small for detail work, large for high output imaging. Surrounding the filament is the focusing cup, a negatively charged molybdenum cup. Its negative charge electrostatically repels electrons and directs them into a focus stream toward the focal spot on the anode. The shape of the focusing cup directly determines the size and shape of the effective focal spot, which is why it matters so much for image resolution. The anode has four things the registry tests. Function: it attracts the accelerated electrons, serves as the target for X-ray production, and manages the heat generated. Material: tungsten rhenium alloy is the standard target. Material: tungsten's atomic number of 74 makes it an efficient X-ray producer. Its melting point of 3,422 degrees Celsius means it can withstand the tremendous heat load. Rhenium is added to the alloy to reduce pitting and surface cracking over the tube's life. The anode Disc itself sits on a molybdenum stem with a graphite backing for heat dissipation. Rotation: the anode rotates at 3000 to 3600 rpm standard, or above 10,000 rpm at high speed. This rotation distributes heat across the entire anode track rather than concentrating it at one spot, which is what allows diagnostic tubes to handle the high MAS exposures needed for abdominal and fluoroscopy work. An anode angle, typically 7 to 17 degrees in diagnostic tubes. The angle determines effective focal spot size. We'll cover that relationship in Lesson 4. Because 99% of electron kinetic energy becomes heat at the anode, heat management is the most critical engineering challenge in X-ray tube design. Heat units, HU, quantify the thermal load. The formula: HU equals kVp times MA times seconds times the generator factor. On this chart, you can see how generator type affects heat unit output for the same technique settings. High frequency generators use a factor of 1.0, they deliver the full calculated heat unit value. Single-phase generators use a factor of 0.7, meaning they're less efficient. More on generators in Lesson 3. 3 charts govern tube heat management and must be consulted before high-demand procedures. The radiographic rating chart shows maximum safe single exposure combinations of kVp, MA, and time. Never exceed these values. Tube damage results. The anode cooling chart shows how quickly heat dissipates between exposures. Essential before fluoroscopy or rapid series imaging. The tube housing cooling chart shows the thermal capacity of the insulating oil housing. Exceeding the housing limit activates an automatic thermal cutout. Your exposure terminates to protect the equipment. And tube seasoning: any new tube or tube returned from storage must be gradually warmed with low-technique exposures before clinical use. Thermal shock to the anode from jumping straight to high-technique work can cause immediate damage. The glass or metal ceramic envelope has 3 roles. It maintains the vacuum. It contributes inherent filtration. The glass itself, the insulating oil, and the port window together absorb approximately 0.5 to 1.0 mm aluminum, equivalent of low-energy photons. And in mammography units, a beryllium window replaces glass. Beryllium has much lower inherent filtration, allowing the soft X-rays needed for breast tissue imaging to exit the tube. The lead-lined housing surrounds the envelope and limits leakage radiation to the regulatory maximum of 100 mrem per hour at 1 meter. 6 QC tests govern the X-ray tube system. HVL measurement confirms adequate filtration. kVp accuracy must be within plus or minus 4 kVp of the indicated value. Timer accuracy must be within plus or minus 5%. MA linearity must be within plus or minus 10% between stations. Focal spot size is verified by star pattern or slit camera. And reproducibility must show a coefficient of variation of 0.05 or less. All tested at installation and annually. 3 registry-style questions on X-ray tube construction. Think each one through before the answer appears. The answer is B, the focusing cup. The focusing cup is a negatively charged molybdenum cup surrounding the filament. Its negative charge electrostatically repels electrons and directs them toward the focal spot on the anode. The shape of the focusing cup directly determines the size and Shape of the effective focal spot. The answer is B. Consult the anode cooling chart and allow adequate rotor prep time. Before any high-demand procedure on a new tube, the anode cooling chart must be reviewed to confirm the thermal load won't exceed capacity. Adequate rotor prep time, 1 to 3 seconds to reach full rotation speed, must be allowed. Before exposing. Premature exposure damages the anode surface permanently. The answer is B. To prevent electrons scattering between cathode and anode. The vacuum inside the glass envelope is essential, because air molecules would collide with and scatter the electrons traveling across the tube, dramatically reducing X-ray production efficiency and damaging tube components. Without the vacuum, the tube cannot function at all. You covered the operating console, the full tube cross-section. Diagram, cathode and anode assemblies, heat units and cooling charts, glass envelope filtration, and QC testing requirements. This is the foundation for everything in the equipment operation. Category. Keep drilling in the practice section.